How are you all doing this morning?
Doing great.
I'm doing good.
All right, so hopefully you guys had a chance to watch the video on instantaneous power and average power. So we're going to jump right into the in-class assignment unless anybody has any questions they'd like me to clear up beforehand. All righty. So this first problem, we have effectively an equivalent impedance. We're not given the network, but we are told what the equivalent impedance of the network is as a function of frequency, where ZEQ is equal to the resistance value divided by the square root of 1 plus omega squared R squared C squared with an angle of the negative arctangent of omega RC. And we're given values for the resistor, 10 kiloohms, capacitor, 200 nanofarads. And we are told that if a current of I of t is equal to 2 sine 377t plus 22 degrees milliamps flows into the network, we want to figure out what the instantaneous power absorbed by the network is. So our generic equation for the instantaneous power absorbed by a network is given by P of t is equal to 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So the pieces of information that we are going to need to figure out are the magnitude of the voltage drop, the magnitude of the current, that's actually given to us, the phase angle of the voltage, and the phase angle of the current. So we are effectively going to work this problem in the frequency domain, even though we're looking to get a time domain equation, because the frequency domain, or analyzing the circuit, or doing the math in the frequency domain, I guess in this case, since there's no circuit to speak of, will allow us to get those pieces of information that we need in the shortest amount of time. So let's start with the current equation, okay? So we have I of t is equal to 2 sine 377t plus 22 degrees milliamps. How can we convert this time domain current into a frequency domain phasor current?
We first have to switch it to a cosine by subtracting 90 degrees from that angle.
Okay, so it would be 2 cosine 377t minus, let's see, 68 degrees. Is my math right there?
Yeah, 68.
All righty. So that means our phasor representation of our current is what?
2 angle negative 68 degrees.
Angle negative 68 degrees milliamps. All right, so we now have Im, and we also have theta I. How do you think we're going to figure out our voltage?
I was thinking we could solve for numerical values of ZEQ given our information.
Okay.
And then multiply those two.
So the suggestion, I believe, is that V phasor is going to be equal to I phasor times ZEQ, which is just Ohm's law in the frequency domain. And that's a perfectly valid way of solving for V. So to that end, our equivalent impedance, ZEQ, 1 plus, let's see, omega in this case is what?
I didn't hear what you said.
What is omega in this problem?
337 or
370
377, my bad.
problem. Radians per second, quantity squared. All right, then we have R, so that's 10 times 10 to the 3 ohms squared. And then we have 200 nanofarads, that's 200 times 10 to the minus 9 farads squared. All right. And then R is 10 kiloohms, so that's 10 times 10 to the 3 ohms. Our angle is negative arctangent of omega, so that's 377 radians per second times R, 10 times 10 to the 3 ohms times C, 200 times 10 to the minus 9 farad. All right, so let's find one of my calculators here.
Do we not have to change that capacitance to a complex? Or can we just leave it as farads?
We should leave it as farad. So let's talk about the units here, right? A farad, let me think about this real quick. It's either an amp second per volt or volt second per ampere. I believe it's an amp second per volt. So if 1 farad is equal to 1 amp second per volt, when we multiply things out, so we're going to have radians per second, where a radian is a dimensionless quantity. So our first thing, omega has units of 1 over seconds. An ohm is a volt per ampere. And then we have farads as ampere second over volts. This cancels, this cancels, this cancels, and this cancels. And we have a unitless denominator, which makes sense, right? Because we're expecting our impedance to be ohms.
Yeah.
So we do not need to change anything into the frequency domain there.
Okay.
All right, so we're going to have 10 times 10 to the 3 divided by the square root of 1 plus 377 squared times 10 times 10 to the 3 squared times 200 times 10 to the minus 9 squared. Oh, my calculator is running out of steam here. Slightly different way. 1 plus 377. So on my calculator, it ran out of memory to be able to do that operation. So 10 times 10 to the 3. So I'm breaking it up into smaller parts. I take the square root of that, I get that, and then 10,000 divided by that, I get 7,984 0.643 ohms with an angle of, let's see, negative inverse tangent negative 37.016 degrees ohms. Did anyone else get a similar answer?
I got the same for the magnitude. I'm doing the angle now.
Alrighty.
I got the same. However, I didn't get. Oh, never mind. Yep, I got the exact same. I forgot the negative on that tan in front of it. I forgot to put that in there.
All right, so now that we know ZEQ, our phasor voltage V is 2 angle negative 68 degrees milliamps times 7.984 angle negative 37.016 degrees kiloohms. And I'm expressing it in kiloohms because I know that a milliamp times a kiloohm is going to give me a volt. So I take negative 68 times I got 15.969 angle negative 105.016 degrees volts. Negative 68 minus negative 37. Yeah, okay, that seems reasonable enough to me. So that means that I now have VM and theta V. So I'm ready to put everything into my expression. So P of T is going to be 1/2 times the magnitude of my voltage, 15.969 volts, times the magnitude of my current, 2 milliamps, times the cosine of theta V, which is negative 105.016 degrees, minus theta I, which is negative 68 degrees. And because I think I'm going to run out of room, plus 1/2 times 15.969 volts times 2 milliamps times the cosine of twice omega, 377 radians per second, times time, plus theta V, minus 105.016 degrees, plus theta I, negative 68 degrees. So if I do the math here, 0.5 times my magnitude, 15.969, times my current, 0.002, gives me 15.969 milliwatts. I multiply that by the cosine of negative 105.016 minus negative 68. So I get 12.751 plus 15.969 cosine, let's see, 754 t minus 173.016 degrees milliwatts for my units. Things seem to be pretty hunky-dory there. So the answer that we got based on our analysis matches exactly the answer that I've supplied to you. So these problems involving instantaneous power, I'm not gonna lie, they're probably gonna be pretty tedious, but it's a cookie cutter recipe. So if we can remember this single equation, we can actually determine the instantaneous power for any circuit element. So I believe in my online lecture that I talk about the instantaneous power in a resistor, capacitor, inductor, all that kind of stuff. All those equations are perfectly valid, but I prefer the generic equation because it works for literally everything. It's much easier for me to remember one single equation than a whole bunch of different ones. So that's just my advice to you. Take it or leave it, as it were. Any questions on this problem? All right, hopefully fairly straightforward. Problem 2, we're told that we have 3 circuit elements connected in parallel, a current source, a resistor, and an inductor. All of the transients have long since died out, so we're assuming that we're operating at sinusoidal steady state, and we want to calculate the instantaneous power absorbed by each element at t is equal to 10 microseconds. So the first thing that I would do here would be to draw the circuit, but probably in the frequency domain. So we would have the current source in parallel with a resistor in parallel with an inductor. Like so. So what is the phasor representation of this current going to be?
$100 angle 0 degrees.
So 100 angle 0 degrees milliamps. I'm going to call that 0.1 angle 0 degrees amps. Because 100 milliamps is 1/10 of an amp. What is the impedance of my 1 kilo ohm resistor going to be?
One kilo ohm.
Exactly right. So the impedance of a resistor is the resistor value itself, and the impedance of my inductance, CL, is J omega L. So that means we're going to have, let's see, times 10 to the 5. So 200,000 times 15 times 10 to the minus 3. So this will be a J 3000 ohm impedance. So since we want the instantaneous power absorbed by each element, we are going to need to know the voltage drop, which I'll call V of t, or actually I should do it as a phasor. And then we're going to need to know the following currents. And these currents I'm drawing based on the polarity of my voltage that I've assumed here. So I want the instantaneous power absorbed by each element. So I'm going to call this current direction down IS phasor. This current direction down IR phasor. And this current direction down IL phasor. So that the current is flowing into the positive polarity terminal of the voltage in each case. So once I know that voltage and those three currents, I can determine the instantaneous power absorbed by all of those elements. All right, so how can I go about solving for any of these three quantities?
Would it be easier to find the equivalent impedance and then do Ohm's law, or do current division and then find the voltage, whichever?
So if we do current division and then apply Ohm's law, that is, we're actually going to wind up, if we combine those two steps together, we would wind up with the exact same equation as finding the equivalent impedance and multiplying by the current. So whichever way floats your boat, because they literally give us the exact same relationship.
I'd probably prefer to do the equivalent impedance first.
Okay, so ZEQ in this case is going to be 1 kilo ohm in parallel with a J3000 ohm. And so this will be, oh, I guess I should write it as 1000 in parallel with J3000. So this would be 1000 plus J3000 ohm. And all right, so 1000 times 3000 I divided by 1000 plus 3000 gives me 948.683, angle 18.435. degrees ohms. And now using Ohm's law, V is 0.1 angle 0 degrees amps times 948.683 angle 18.435 degrees ohms should give me 94.868 angle 18.435 degrees volts. Anybody have any problems with that?
I don't think so.
Alrighty. So now that we know what our voltage is, how can we determine our currents?
Ohm's law.
Yeah, Ohm's law. So IR is going to be V divided by 1000 ohms. So that's going to be 94.868 angle 18.435 degrees milliamps. That one's easy enough. Because 1000 ohms is the same as 1000 angle 0 degrees, so we know that our angle shouldn't change. IL, actually require a little bit of math. So that's going to be our phasor voltage divided by J 3000. So I get 31.623 with an angle of negative 71.565 degrees. Milliamps, how do we determine IS?
KCL.
So you're right, but there's an easier way. We know the current flowing up is 0.1 angle 0. So what's the current flowing down?
Oh, that would be 0.1. That'd be negative 180 or 180.
They're identical, so it really doesn't matter which one you choose. Let's just say 180 degrees. So for whenever it's the plus or minus 180 degrees, because you're using effectively a negative sign, those represent the exact same thing. So it really doesn't matter which one you choose. So you can't get it wrong. I just want to be clear about that. Well, all of these other ones are in milliamps, so I guess I'll do this one as 100 angle 180 degrees milliamps. Okay. So we now have enough information to determine our instantaneous power. I'll probably actually only hand work out one of these because the method is exactly the same for all three of them. So let's just calculate the power absorbed by the resistance at T is equal to what? 10 microseconds? Yeah. So that's going to be 1/2 times the voltage drop, 94.868 volts, times the current, magnitude of the current, which is 94.868 milliamps, times the cosine of the angle of the voltage, 18.435 degrees, minus the angle of the current, which is 18.435 degrees. So we know that this bit right here is just going to go to 1 plus 1/2 94.868 volts, 94.868 milliamps, times the cosine of twice omega, so twice 2 times 10 to the 5 radians per second. Okay, so if we carried on here, like if I put 10 microseconds here, multiplying these three numbers together would give me an angle. But would that angle be measured in radians or degrees?
Right now, it's like radians.
Right. And I know that my phase angle bit over here is in degrees, right? I'm going to have theta V 18.435 degrees plus theta I 18.435 degrees. And I'm going to close off my parentheses. So the issue that you're going to have is that your calculator can't work in radians and degrees simultaneously. So what I'm going to do here, before I multiply by time, I'm going to multiply by a conversion factor. So there are exactly 180 degrees for every pi radian. So that cancels my radians out, and I'm having degrees per second multiplied by my 10 microseconds. And now everything inside the cosine function is expressed in degrees. So if you didn't notice that, and an awful lot of students don't their first few times trying to work through these, it's highly likely that you would have gotten an incorrect answer. And the only reason your answer was incorrect is because you're adding radians to degrees inside your calculator, and it can't do it. So we need to implicitly do some form of conversion. So with that in mind, we're going to have 0.5 times 94.868 times 94.868 times 10 to the minus 3. So this is 4.4999, let's call it 5, plus 4.5 multiplied by that cosine bit there, where cosine of 4 times 10 to the 5 times 180 over pi times 10 microseconds, which is 10 times 10 to the minus 6, plus 18.435 plus 18.435 gives me negative 0.0688 and some change there. Gives me 4.190 milliwatts. So let's check. 4.190 milliwatts. Great. So, why won't this thing scroll? If I wanted to do the power absorbed by the inductor, it would be this exact same expression, except that I would change everywhere I see 90.868 milliamps, I would change to 31.623 milliamps, and I would need to worry about the phase angle of the current as well. So at this point, it's just literally plugging stuff into this generic equation and then pressing the equal sign on our calculator. So do I need to go through the motions of finding the inductor current, or excuse me, the power absorbed by the inductor and or the power absorbed by the source?
How did you get to milliwatts instead of watts? Like,
Because
the answers in watts.
Let me double check what I did here in my calculation. Okay, so in my calculation, I did do 94.868 times 10 to the minus 3. So you were 100% correct. It should be watts. I got milliwatts because I saw volts times milliamps and forgot I had accounted for it in the calculator. So I apologize for that. Any other questions on this problem? All righty. So for our last problem here, we want to determine the average power absorbed by each of the elements in this network. So that means that we're going to need, and we're looking for power absorbed. So let's define some voltages here. So this is what we'll call VR. And this voltage will be VC. We're going to define some currents. So this guy will be IR. This guy will be IC. And this guy down is going to be ICS. And the reason why I'm choosing to represent the current source voltage down is because the 4 ohm resistor is in parallel with the 12 amp source. And so I want a current that's flowing into the positive polarity terminal so that I can get the absorbed power. Alrighty, so with that in mind, how could we go about determining any of these quantities? Anybody have any ideas here?
Wouldn't ICS just be 12 angle 180 degrees?
Okay. So our phasor current ICS, we know for sure is just going to be 12 angle 180 degrees amps. All right. What about the other 4 quantities that we need? How could we go about determining any of those?
We could do nodal analysis.
Okay.
I'll go first.
So let's consider that. So the suggestion by Mr. Munoz is that we do nodal analysis. So let's think our way through that. I'm going to choose this bottom node as my reference, and I'm going to call this guy up here node A. So by the looks of it, that's the only unknown voltage in my system, right? Because the voltage at this node over here is 4 angle 30 degrees volts with respect to ground because I have a super node effectively. So I feel like that's a pretty solid choice. My first instinct personally was to do superposition because then I could simply do current division and voltage division to get all the quantities I want, current division, voltage division, and Ohm's law. But I think your suggestion of nodal analysis, where we really only have one equation, one unknown, is shorter. So good eye. So if we apply Kirchhoff's current law at that node A, we are going to have, let's see, so we're looking for this current, and this current. So my current directed to the left is exactly what we have called ICS. So that's going to be 12 angle 180 degrees. We could also call it negative 12 angle 0. Those represent the exact same thing. For my current directed down, I'm going to have phasor voltage VA divided by 4 ohms. And for my current directed to the right, I'm going to have VA minus 4 angle 30 degrees volts divided by minus J2 ohms is equal to 0. And actually, now that I'm thinking about it, it might be a little bit easier to express this as negative 12 angle 0 degrees amps because when we move the constants to the other side of the equal sign, which will be our next step, it'll move easier. So when we move our constants to the right-hand side of the equal sign, we're left with VA divided by 4 ohms plus VA divided by minus J2 ohms is equal to positive 12 angle 0 degrees amps plus 4 angle 30 degrees volts divided by minus J2 ohms. Right? That's just simple algebra. I can now factor out VA from the left-hand side, which leaves me with 1 over 4 ohms plus 1 over minus J2 ohms is equal to 12 angle 0 degrees amps plus 4 angle 30 degrees volts divided by minus J2 ohms. And from this, VA is equal to 12 angle 0 degrees plus 4 angle 30 divided by minus J2 divided by 1 over 4 plus 1 over minus J2. And that's something I can put in my calculator and it can do the math for. So I couldn't put this, my original expression into the numerical solver or anything like that. It would give me an error because it's using complex numbers, but we can do simple algebraic manipulation and get a result here. So 12 angle 0 plus 4 angle 30 divided by minus 2i. I'm going to store that as x. Then I have 1 over 4 plus 1 over minus 2i. I'm going to store that as y. And then x divided by y, I get 19.920 angle negative 54.487 degrees. Volts. Did anybody else get something similar?
Yes, sir. That's what I got.
Cool deal. All right, so now that we know that nodal voltage VA, how much other information do we have? Well, VA with respect to ground is the exact same voltage as VR, right? So VR is equal to VA is equal to 19.920 angle negative 54.487 degrees volts. And so we can then determine IR, which is going to be VR divided by 4 ohms. Which is 4.980 with an angle of negative 54.487 degrees amps. How could we go about finding VC?
VA minus the voltage source.
That's exactly right. So VC is VA minus 4 angle 30 degrees volts I get to be 19.937 with an angle of negative 66.006 degrees volts. And IC is simply VC divided by negative J2 ohms. Which I get to be 9.968 angle 23.994 degrees. And I think that pretty much gives us everything. All right, so average power is just the DC portion of instantaneous power. So the average power absorbed by our current source, let's call that, so we're gonna run out of room here. PCS is the voltage drop over our current source, which is, so it's going to be 1/2 times the magnitude of the voltage drop, which is 19.920 volts, times the magnitude of the current, which is 12 amps, times the cosine of theta V, negative 54.487 degrees, minus 180 degrees, 19.920, 12 times cosine of negative 54.487 minus 80. So I get negative 69.428 watts. I'm just making a ton of noise in the background and isn't muted. Just a heads up. And we can use the same exact expression for all the other ones. So for instance, our resistor is going to be 1/2 the voltage drop over our resistor, 19.920 volts. The current flowing through our resistor, 4.980 amps, times cosine of theta V, negative 54.487 degrees, negative minus theta I, which is negative 54.487 degrees. So 0.5 times 19.920 times 4.980 is positive 49.601 watts, and so forth and so forth. So we could do all of these, again, just using the same generic equation. So I will leave the last, let's see, there's 2 elements up to you guys. Okay, so that's instantaneous power and average power. So what the next couple of videos that you guys are going to watch are about. The first video that you'll watch is on effective values. And the reason that you need to use, understand what effective values are is because the complex power uses effective values in all of its calculations. So as a brief precursor to your effective value lecture, let's talk about what an effective value really means. So I'm assuming you guys are all in some sort of civilized place where you have some sort of electrical outlet near you. What is the voltage present? Like, what is the voltage supplied by that outlet? Anybody have any idea?
I have no earthly idea. That's actually, I would like to know that.
Does anybody else care to venture a guess? Has anybody ever heard an electrician or anybody talking about the voltage supplied by an outlet in your home.
Is it 12?
It is not 12, but it is a multiple of 12. All right, so let me open up something here. Edit, no. So you might have some electrical things in your home that run off of 12 volts. And you can get 12 volts very easily based from the regular outlet voltage using a transformer, which is why a lot of smaller consumer electronics run off of 12 volts. All right, so I'm going to draw probably a pretty terrible looking thing. So I believe the long one is on the left, short one is on the right, and then there's usually something like this. So this is a probably pretty crappy drawing of an electrical outlet, one of a single receptacle. And in your home, most likely you have what are called duplex receptacles, where it's just two of these guys stacked on top of each other. So in your home, I'll do it this way. These aren't the wire colors that are typically used in your home, but I can't draw a white line. So you would typically have a red lead connected to the polarized plug. And this is what's called hot wire. And you would typically have, I guess I'll use black. The lead connected to the shorter rectangular terminal here is what's called the neutral wire. In most homes, the hot wire is actually black and the neutral wire is white, but again, I can't draw a white thing. And then you would see a green wire, and this is ground, like actually tied to earth ground. And that ground connection isn't really part of most circuits. It's an external connection to literally the surface of the earth through a metal rod driven into the ground. And it's a way to dump off excess energy. Outside of your junction box or your breaker box or whatever you want to call it, you'll typically see that your neutral wire or your neutral conductor is tied to your ground. But inside your home, the neutral is a different thing. All right, so the commonly associated voltage across the polarized terminals of your receptacle is commonly referred to as 120 volts. You may hear it as 110 as well in some areas, but it's typically 120 volts. In Europe, it's 230 volts. In Japan, it's 100 volts. Not sure what other countries use. Those are the only, the US, the European Union, and Japan are the only places that I've had to design electronics for. So those are the only voltages that I know off the top of my head. Well, this 120 volts right here is not the actual voltage that's generated across the terminals of this, because this would imply that there is 120 volts of DC power that's being supplied by our receptacles. And power in the United States and most of the civilized world is distributed using alternating current. So instead of 120 volts, what we would actually have is that voltage V of T is, I think it's 169.7, but let me double check. Yep, 169.7 cosine 120 pi t here in the US plus some phase angle theta V volts, where that phase angle depends on when we start measuring things. This 120 volts that I've circled in green is the effective value of this periodic waveform. What that means is that this voltage, V of t is equal to 169.7 cosine blah, 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 delivers the exact same amount of average power to a resistor as a 120 volt DC source would. So that's what effective values mean. So the reason why our complex power relationships, which were developed by electrical engineers in the early 1900s, use effective values is because it would be enormously tedious to have to carry around all of this information for every single calculation. Instead, we use an effective value so that we can do simple DC calculations to determine what size of wire needs to go in your home, which then enables us to calculate proper breaker sizes and all that kind of stuff. So all of the work of an electrician or somebody working in the power industry is based off of these effective values. So that's why we're going to start there before we jump into our complex power relationships. And this is effectively just the first, I don't know, 3 or 4 minutes of that video, so I guess you can skip ahead. All right, any other questions before we duck out for the day? All righty, well, we've got a whopping 2 lectures left, so thank you for your perseverance, and I will see you guys on Thursday.